Hey everybody, so today I'm going to be going over some virtual memory questions, and because it's actually a pretty complicated topic, and it's also a good topic to know. If you ever take 162 in the future, it's good to know. So I'll be going over some problems from the Gorilla worksheet, and yeah, CS. Well, I guess not everyone has my sense of humor. So with that, let's get started. So when you look at a virtual memory question, there should be three things on your mind. How big is my virtual address? How big is my physical address? And how many bits do I need for page offset? Well, lucky for us, that's the first thing they give us. You run the code in the system with the following parameters. 4 gigabytes of virtual address space. Okay, so what does that tell me about how big my virtual address space needs to be? Well, 4 gigabytes, that's 4 times 2 to the 30 bytes. If you don't remember that, that's on your MIPS green sheet. If you don't know how to look it up on your green sheet, then you should probably review midterm 1 stuff. So with that, so that's 2 to the 32 bytes, right? And how many bits in an address do I need to address 2 to the 32 bytes? Well, it's just the log of how many bytes there are, right? So it's just 32-bit virtual addresses. Does it make sense? Hopefully it does, because this should be similar to when you were doing the tag index offset breakdown for cache, if you remember that. So yeah, 32-bit virtual addresses. And physical memory is 1 GB. So how big are our physical addresses? Well, our physical addresses, so our physical memory space, our RAM, is 2 to the 30, my bad, and you need 30 bits to index that, right? So you have 32-bit physical addresses. Does that make sense? Right? Because we did the same thing as we did for virtual addresses, only with 1 GB instead of 4 GB. So we have 30-bit physical addresses. And how big does our page offset need to be? Well, it tells us 2 KB. What's 2 KB? Well, that's 2 times 2 to the 10 bytes. That's 2 to the 11 bytes. How many bits do we need to uniquely index 2 to the 11 bytes? Well, it's just 11 bits. So 11-bit page offset. Make sense? Pretty good? Okay, so now we have our vitals for virtual memory. We need these three things in order. We need these three things in order to break down our addresses. Make sense? Good. Okay. So a generic, that's not what I want. A generic address is essentially a page offset and then a virtual or physical page number. So this is the format of an address. Actually, hold on. That actually might be a little confusing at the moment. So I'm gonna just. It's a page number and then a page offset. So the idea is first we have to know what page we're looking at. Okay, we have to know what page we're looking at. Once we find what page we're looking at, then we can use the page offset at the bottom to tell us where we are in the page. Make sense? It's kind of a logical system. I mean, yeah, it is a logical system because you look up the page, what page are we on, and then once you're in the page, you look up, okay, where am I within the page? Make sense? So in order to find out how many bits we need for the virtual page number, the physical page number, well, it's quite easy. We just use these vitals. These 3 vital facts that we have up here. There we go. So entire thing, this virtual address, is 32 bits. Make sense? So let's move that up here. This is 32 bits total. Does that make sense? Okay. And we're going to have physical address. Come on. Be a little more cooperative. There we go. Okay. We have a physical address, and the physical address, you'll notice, has a different length than the virtual address. And you might think, well, that's kind of weird, right? But it's because physical memory, main memory, is smaller than the virtual space. The OS promises 4 GB of virtual memory, but it only has 1 GB in the RAM. So then I guess the obvious question is, but then where does the extra memory go? It goes to disk. Disk has infinite capacity, basically. So disk is the dumping ground for all the leftover pages. But we don't want to do that too often, because disk is really slow. So we want to just, if we can do it, we want to try to only use main memory and then resort to disk if we have to. So that's why our physical address is shorter than our virtual address. Does that make sense? Because physical space is smaller than virtual space, so we need fewer bits to index it. All right, now here's a key point. Pages, whether they are virtual pages or physical pages, have the same size. A virtual page is 2 KB. A physical page is 2 KB. That is why virtual and physical can talk with each other. They talk using pages. And pages are the same size because if they weren't, virtual and physical would not be able to talk with each other. They would not be able to transfer, pages between each other. So, if pages are the same size in virtual and physical land, and the addresses have the same format that I described earlier, how many lower bits do we need to index, to offset within the page? Well, we have our page offset here, and we have our page offset here, and in both cases, it's going to be 11 bits. Sound good? These lower 11 bits are the page offset. So we have to find what page we're in. That's our page number. And then once we find the page, then we can use the lower bits to tell where we are. And that should make sense. If not, then review the cache concept again. It's kind of similar, except it's kind of similar, like our page numbers are kind of our tag, and our page offset is our block offset in this case, and there's no index. So it's a very similar concept. Okay, so these bits are a page number, and these bits are a page number. Notice, I said pages are the same size in virtual land and physical land, but virtual land and physical land are different sizes. So the page numbers, there's going to be different amounts of pages because we can't change how big an individual page is, right? So in order for these to have different sizes, well, we have to change how many pages there are. In order to do that, we change the page number. So here, this is our virtual page number, or VPN. And for our physical address, we have the physical page number, or PPN. Now, notice, the virtual page number is the rest of the address that's not offset. So we just use simple subtraction, and that gives us 21 bits. So the answer, I'll put that in a moment. And for our physical addresses, 11 bits are taken up out of the 30 by page offset. So using simple subtraction, again, our physical page number is 19 bits. And this makes sense, because if you think about it, the page offset represents how big an individual page is. And we have 2 to the 32 bytes in the virtual space, and each page is 2 to the 11. So there's going to be 2 to the 21 pages by division. 2 to the 32 divided by 2 to the 11 equal 2 to the 21 pages. And analogously here, there's going to be 2 to the 19 pages in physical land. So their answer is going to be 19, or no, wrong one. It's going to be 19 for physical, and it's going to be 21 for virtual. Does that sound good? Is everyone okay? Okay, good. That was the easy part. Now we have to do the actual question. Okay. All right. So you know how you can serialize, or you know how you can make a matrix. Oh, that's not what I want. Oh, okay. You know how you can make a matrix. Doop, 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 right? That's a really badly drawn matrix, right? You know how instead you could draw it as a one-dimensional array, right? And it just goes on off the edge of the page, or up to 16 entries. And instead of doing row, column, now you do row times this length of a column, so that'll get you up to your row, and then, or let's do it here for convenience, and then you offset by the column. Does that sound good? See what they're doing here? You might see it already, but all right, let's erase this. Okay. You might see it already, but okay, so what does this code do? Well, there's some details, but essentially what this code is doing is it's just iterating through the array. It's iterating through it in a certain way, but it's basically just iterating through the entire array. So what is this stretch? What does it mean? Oh, that's not what I want. What is a stretch? What does it mean? What is it doing there? Well, in the end, sum is going to be a sum of every element in the array, and product is going to be a product of every element in the array. So why do we bother with this stretch thing? I'll show you why. So, okay, let's flip this. Suppose we had a, okay, where did it go? There we go. Okay. Suppose, okay, so the real array is 2 to the 25 ints. But let's just suppose, for sake of argument, that it's 8, right? Right, we have an 8 int array, right? Does that sound good? And let's pretend that we had a stretch of 2. Again, just for sake of example, okay? And size equals 8 ints. I'm good? Okay. So this is going forward, and this is going backward. You can tell that intuitively, right? Okay. So let's analyze with an array of 8 ints and a stretch of 2, what's going on. Because, okay, yeah, let's ignore the real size and the potentials for stretch, okay? All right. So, actually, let me just copy paste this. Or actually, yeah, let's just copy paste it over here. Okay, does that sound good? So I copy pasted the 2 innermost lines over there. So let's take the first loop. That's the green underlined loop, right? What is it going to do with our 8 element array? We're going to go to element 0, right? And then we'll advance to element 1, right? And then we'll stop because our stretch is 2, right? So we went forward by 2. All right. Let's take a look at our second loop. Let's make this a purple loop. Our purple loop will start at element 1, go down to element 0, and then stop because now it's less than or equal to 0. Sound good? I think you're going to start seeing the pattern now. So when so now at first I was equal to, actually, you know, maybe I should have put this up here too. So at first I was equal to 0, right? This is when I was equal to 0. This, right? What about when I equals 1? Well, when I equals 1, we're going to start at 1 times 2 plus 0, 2, and then we're going to go up. Hold on. Yeah, we start at 2, and then we advance to 4, or 3, my bad. 2 and then 3, and then notice, j was 0 here, and then j was 1 here. And so we stop because stretch is 2. And again, notice in the second loop, we start at I equals 1 times stretch 2. So 1 times 2, that's 2. Plus, what's j? J is 1. So 2 plus 1, that's 3. 3. And then we go down. Now j is 0, so we stop. Huh. Do you notice something? We're going to do this every I. This access pattern. And now, here's where the real insight comes. Now, we're going to take this. So up until now, the array is one-dimensional, all right? It's one-dimensional. But we can reinterpret, because of this notation, the I times stretch plus j, we can, let's see if we can actually move these around nicely. We can reinterpret this like this. Do you see now? This is what our access pattern looks like for a stretch of 2 and 8 ints. Do you see it stepping through a small example? So you can intuitively reason that, nope. You can intuitively reason that our actual, for our actual array, we're going to have an analogous pattern. So one thing I want you to notice is how wide is each row? Well, it's stretch 1, 2. It's equal to our stretch of 2. Now, we have our actual array. And now, so originally our array is this really long one-dimensional thing, right? But now we're going to reinterpret it as a matrix. Yeah, it's kind of cumbersome drawing on a computer, so I hope you forgive me for being a little lazy. ... So this is a matrix, essentially. Boop. 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 All right. We have our matrix and ... right? It is, the rows are as long as stretch. Does that make sense? Because think about it. when you do a matrix when you try to interpret a one-dimensional array as a matrix, you do row number times the length of a row plus the column number. Does that make sense? And J goes along here. It iterates within rows, and then I, and you'll see why I drew a bidirectional arrow in a moment. I goes down the rows. Does that make sense? So within a row, okay, here we go. Within a row, let's just pick this random row in the middle, okay? Some random row in the middle. And I'm going to make it a little extra big to fit some stuff. Okay. So, let's make the, no, I want a different, I want red. Okay, I want red. Let's make the I outer loop, yeah, let's just make that the red loop, okay? When we iterate through I, we're going to go down the rows. Does that make sense? Does that make sense? Because think about it. Whatever we're doing inside the loop, like, okay, we're going by columns, and then we're going back and forth, and I'll explain it in a moment. But essentially, I is just iterating through the rows, down the rows. Does that make sense? Okay. So within the one loop of I, the green loop will go forward. And the purple loop, once the green loop is done, the purple loop will start all the way at the end and go back. And then we'll repeat and do this again for another row. So if we had the row here, then we would do the same thing. We'd go forward, and then we'd go backward. And then we'd do the same thing over and over again. Does that sound good? Okay. It's very important that you understand the access pattern behind the array. Because once you get the access pattern, then the rest of the questions become really easy. Make sense? Okay. So, armed with our knowledge of the access pattern, okay, armed with our knowledge of the access pattern, now we can tackle B and C. Okay? So, what are we doing in green? Well, you can, okay, we start with a cold cache, all right? Does it explicitly say it anywhere? Well, it doesn't explicitly say here, but usually, yeah, you start with a cold cache, and if it doesn't explicitly say, then you can ask a TA on the final. But, so our cache has nothing in it. So when we go through everything for the first time in the green loop, we're going to get compulsory misses. We've never seen this row before. Because it just marches on forward. The J, it goes forward and backwards, so we're going to have to do a little more advanced analysis, but I just keeps on going forward. So whenever we first do a row in the green loop, we're going to get some compulsory misses. Now, notice that the, okay, because stretch has to be a power of 2, which I'll explain in part C. Essentially, our compulsory miss rate in green is going to stay constant no matter our stretch. The purple loop is going to be the one that we care about. So I'll just explain the green one for just a moment. So we have 8 bytes in a block. And look, we have a char array, so we don't need to worry about like ints and stuff, right? Okay, that's good. So we're gonna, when we go in the green loop, so this is for the green loop, we're going to compulsory miss the first element in a block, because a block is 8 bytes, right? So we can fit 8 elements in a block. we're going to compulsory miss the first byte, the first char, and then we're going to hit everything else. Right? And this doesn't depend on stretch. We're going to get this 1/8 compulsory miss rate on our green loop, no matter our stretch. Because then in our next block, in our next block, then we just do the same thing. That we have our compulsory miss, and we have our hits from the blocks, and that's very easy to analyze. Is everyone with me? Okay, so the green loop is not going to be affected by stretch. Well, that kind of implies that the purple loop is affected by stretch, right? Okay, so remember the earlier example. The first element in a block is going to be a compulsory miss. Or I should say 0th element, I guess, to be more precise. Every subsequent access is a hit because we already loaded that block. Does that make you think why the purple loop might change depending on stretch? Green, as it goes along, excuse me, how do we do this? Wait, why is this not working? There we go. As the green loop goes along, it loads all these blocks into cache, right? Let me see if I can move it downstairs. There we go. All right. Yeah. So when the purple loop goes through, when the green loop goes through, the green loop is the first loop within the row. So we have a miss, we have a miss, we have a miss, we have a miss, so on and so forth, right? If stretch is small enough, think about it. If stretch is like really small, let's say it's like stretch is like 32, right? It's a really small thing. 4 blocks are obviously gonna fit into 32 kibi, right? I don't want to move that. So all of these will stay in the cache. So when the purple loop goes through, literally everything is a hit because we already loaded everything into the cache. We don't have compulsory misses anymore. When the purple loop goes through, we've accessed everything in the row because of the green loop. So we don't have an excuse anymore. We don't have compulsory misses. If we ever have misses in the purple loop, it's either going to be capacity or conflict misses. But we won't have compulsory misses in the green loop, in the purple loop, because the green loop has already seen everything that the purple loop is going to see. And for small stretches, all the blocks that the green loop loads will stay in the cache. Does that make sense? Okay, good. Now imagine what would happen if stretch was too big. Like, what if these rows were really, really long and green just cycled through a ton of elements? Well, then we're going to have capacity. When we do the purple loop, if the green loop went through too many and stretch was too big, then technically we've seen everything before, but it won't fit in our cache. So the purple loop will have capacity misses. Because even though we've seen it before, so they're not compulsory misses, we still miss because they got kicked out of the cache. So they're going to be capacity or possibly conflict, but it turns out they're capacity misses. So what does that say about stretch? Well, notice how I said if it's too big, if stretch is too big. Well, what is a stretch that's too big? Well, here we're just accessing all the elements literally sequentially, order by order in green. We're not skipping. We're not skipping around. We're literally accessing them sequentially. So the four-way associativity doesn't matter. When you're accessing sequentially, when you're accessing sequentially and you're accessing a multiple of the cache size, then essentially like associative and fully associative, like they're just going to behave the same way. So essentially, you can think of the purple loop as having capacity misses. It's a little bit of a leap of logic, but you think of it as, let's say our cache could only hold 2 blocks. Or actually, is that a good analogy? Let's say our cache could only hold a limited number of blocks, and we were accessing sequentially. Boom, 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 right? Because of the way our access pattern works, eventually we're going to start kicking out the oldest blocks. And it just happens that even though this is four-way associative, because we access the earlier index blocks earlier, we're going to kick out essentially the same way as if they were fully associative for this particular access pattern. So that means that we're limited by our cache size. Does that make sense? Okay, maybe it makes more sense once you think about it. If you access fewer than the cache size elements in the array at a time, aka stretch is smaller than the cache size, then everything from the green loop will fit in the cache. Does that make sense? If stretch is smaller than the cache size, everything in the green loop will fit into the cache. Because the cache is smaller than stretch size, my bad. The stretch size is smaller than the cache, so the row will fit. And so it's because the entire row is in the cache, when we go cycle back, we're not going to have any capacity misses. We'll have a 100% hit rate for the purple loop. But if stretch is too big, if stretch is bigger than the cache size, then now the entire row won't fit. We'll have to make evictions. And if we make evictions, then there'll be some missing blocks, even though we've seen them before, which means that the purple loop will have capacity misses. All right. Does that make sense? So the answer to B is the cache size, which is equal to 32 kibi. Does that make sense? Because essentially, what stretch is doing is it's accessing an entire row at a time and then reading it back. So we want the entire row to fit in the cache. If it's too big, then the entire row will spill out of the cache, and then we'll have misses in our purple loop. And if it's smaller than cache size, if it's smaller than or equal to the cache size, the entire row will fit in the cache, so we'll have 100% hit rate in our purple loop. So stretch size is basically controlling how big our rows are and how many, how much we access at a time per row, essentially. Does that make sense? Okay, I hope that was a little clear. Okay. Now we do something analogous for the part C, except now our unit is pages. We're not dealing with blocks anymore. We're not dealing with these 8-byte blocks. Now we're dealing with 2 kibi pages. So we have an 8-entry TLB, all right? So that's, oh, hold on. We have an 8-entry TLB, right? But actually, it's 8 minus 1. Because, as it says in the problem, here we go. Here, it's very important. The code takes 1 page. And you can basically assume that the code will basically not be evicted, because think about it, every MIPS instruction or whatever this compiles into is going to load from code. So code is going to get used a lot, like literally every line your program runs. So it's basically like just going to eat up a TLB entry permanently. So in reality, that means we have a 7-entry TLB. Does that make sense? Okay. So keep that in mind. Really 7-entry TLB. Does that make sense? Okay. So, all right. So, here's the intuition. Every time, okay, so now instead of dealing with blocks, earlier we dealt with blocks, now we're dealing with pages. So here's the idea. If we overfill the TLB, if we access so many at a time in a row, like we access more than 7 entries, more than 7 pages per row, so the green loop like traverses more than 7 pages, then we're going to have to kick out an old TLB entry. And if we have to kick out an old TLB entry, well then we're going to have TLB misses. So let's draw a simple, oh, that's not what I want. Here we go. So the code page, no, you can't have that one. But the rest of it, we can. So if you think about it, if we go through up to 7 pages in the green loop, then when we read it back in the purple loop, we won't miss because they'll all still be in the TLB. But if the green loop is too big, now, we're outside the TLB. Now we're gonna have misses in the purple loop because we're traversing too much. Okay, now here's where the little trick comes in. So earlier I had mentioned that stretch needs to be a multiple of 2. So basically our choices for stretch are 1, 2, 4, 8, and la-di-da, right? Notice that 8 is bigger than 7. If we had 8, we'll have 1 page that we have to evict from the TLB, and then when the purple loop goes back, it'll miss on that page. So 8 is no longer a valid option. And the reason we have to make it a multiple of 2 is because this here, array size divided by stretch, array size is a 2 to the 25, so stretch has to be a power of 2. If stretch is not a power of 2, it won't divide array size into an integer, and this for loop won't make sense and won't behave correctly. So stretch has to be a multiple of 2. So we said we can't do 8, because we could have done 8 if we didn't have this code page. But code is memory too. Code takes up space. If you don't believe that code takes up space, open up one of your 61c project folders to convince yourself that code takes up space. So it takes up 1 page. So we only have 7. So if we did 8, we'd go through. We'd have to evict the when we load in the last TLB entry, we have to kick out 1, and then that causes a miss for the purple loop. So what's the biggest allowable value? Well, it's 4. Now, what do these represent? What do these numbers represent? Well, they represent pages. Because think about it, you only need to load in a TLB entry per page. Per page. So if we have a maximum of 4 pages and each one is 11, 2 to the 11, then that gives us 2 to the 13 bytes, which is 8 kibi. Does that make sense? So the answer to C is 8 kibi. Does that make sense? Yeah, because think about it. You only need to load in the TLB entry once per page. Well, I mean, if you have misses, then but for the green loop, we have one compulsory TLB miss, and then a bunch of TLB hits thereafter because now we put it in the TLB. So we only need to do the TLB load, like from the miss, once per page. And we have 4 pages, so 4 times 2 kibis for each page. That's 8 kibi total. Sound good? Okay. All right. For any value of stretch, what is the fewest? Okay, so this question is kind of poorly worded, and I don't think it's very well written. Part D. Basically, they mean for any value of stretch. They mean okay. So intuitively, we know from like part B. Okay, this is related to the cache, not the page table, but intuitively, you know that making stretch bigger is bad. So if we make, okay, so basically you know that probably the worst case scenario is when stretch is the maximum, all right? So basically it says for any value of stretch basically means like the worst case scenario for stretch. And intuitively we know that's going to be the biggest one because we notice if we make stretch too big, we get problems. Like cache misses and TLB misses. Now we're going to get page faults. So basically they mean, just think of this as like worst case scenario, which translates to maximum value of stretch, okay? Okay. What does that mean? Well, let's assume that we start with a cold RAM. So we're gonna get a bunch of we can get a bunch of we're going to get a bunch of compulsory page faults the first time we do things. So, so what's the biggest value of stretch we could have? Well, the biggest value of stretch is just 2 to the 25. That's the maximum allowable. If we had any bigger, so basically what that does is, remember this, the matrix interpretation? Now we just literally just collapse the matrix back into the original one-dimensional array. We just have one row, and the row is as big as the original array. Good? Okay. So, what's the fewest number of page faults that we could generate? Well, in an ideal scenario, we only have compulsory page faults. Let's see, did they give specs on? Let's see, 2 to the 30. Oh, right, okay. All right, okay. So we have enough RAM in this question to store the entire array in memory. So we will only have compulsory page faults, okay? To convince yourself, our matrix is 2 to the 25 bytes, right? And that is less than the 2 to the 30 bytes we can hold in physical memory. So can hold entire, so we can hold the entire array in physical memory. So we only get compulsory page faults. Yeah. In the best case scenario. Yeah. You'll learn more about the details in 162. Okay. So we'll have a bunch of compulsory page faults every time we access a page. All right, so what is that? We'll have one compulsory page fault for the code page. And then, okay, we have 2 to the 25 bytes, right? Okay, that's how many accesses we do. But how many pages are we accessing? Well, the amount of pages that we access is 2 to the 25 divided by the page size. So it's the amount of stuff we're accessing divided by the amount of stuff in a page, and this will give us the amount of pages that we're accessing. So that's 1 plus 2 to the 14. So that's just 2 to the 4 times 2 to the 10, or 16 Kibbe faults. Kind of awkward way to say it, but so 16 key faults, or 16 times 1024 faults, if you want to think of it that way. Notice how I just kind of ignored the code page, because 1 plus 16,000 whatever is not going to matter. So yeah, we just dropped the code page fault. So does that make sense? I hope that makes sense. The idea is we just have a bunch of compulsory page faults. So we determine how many pages we access throughout the lifespan of the program. And yeah, the maximum stretch would be 2 to the 25. So this is the amount of stuff we're accessing divided by 2 to the 11, because that's our page size. That'll give us the number of pages. Something that I've personally found to be a very helpful tactic in 61c is dimensional analysis. So here you can see 2 to the 25 bytes divided by 2 to the 11 bytes per page equals 2 to the 14 pages, because bytes, they cancel, and you're just left with pages a unit. Sound good? Okay. Now on to the last question. This is kind of more of a conceptual question. So suppose that we had 256 byte pages, and our code is 64 instructions long. And so how would performance change if we loop unrolled by a factor of 8? Okay, so I really like this question because it's actually pretty clever. It goes to some it explains a little bit why we don't just loop unroll like everything. Like, why does loop unrolling not cure cancer? You know, oh my God, it's just this simple thing can make our code faster. So why don't we just do it all the time? Loop unrolling the intuitive explanation is loop unrolling increases the size of your program. And remember I said earlier that program takes up memory too? So if your program takes up more memory, it starts competing with the memory that you're actually trying to use for data. So now we'll actually see that in this question. So if it's 64 instructions long, you know, that's and we loop unroll it 8 times, right? So our code size is going to be approximately 64 times 8. Obviously, there's going to be some overhead, but the majority of our program is spent in the for loop. So we can safely say that we're gonna octuple our code size essentially. So that's 2 to the 6 times 2 to the 3. Is it? Hold on. 2 to the 6 times 2 to the 3 equals 2 to the 9th. Hold on. My bad. Okay. Sorry. I just multiplied at the wrong time. So so we have 64 instructions, right? Okay. So let's just determine the default code size. All right. No loop unrolling. All right. How big is our code in the beginning, right? And it's going to be 64 instructions times 4 bytes per instruction. Does that make sense? You learn in MIPS that instructions are word, or the size of a word, and words are 4 bytes. So that's going to be 2 to the 6 times 2 to the 2 which is equal to 2 to the 8 bytes, which is equal to, oh hey, would you take a look? Our code fits in exactly one page. So would you take a look at that, right? All right, okay, so now we know it's one page for no unrolling, right? If we loop unroll, we'll approximately, so our new code size will be the original code size times 8, because we loop unrolled by a factor of 8, and most of our code is spent in the for loops. So if we loop unrolled, then that means that our code is now 8 times bigger. So that's around 8 pages for our new code size. Sound good? Okay. Okay. Here's the problem. We have an 8-entry TLB. Our code now takes up 8 entire pages. Do you see the issue here? Oh, hold on. So we have our 8-entry my apologies for the messy TLB. We have our 8-entry TLB. We originally had one code page. Now we have 8 code pages. Oops. Where does our data go? So, data address translation. No. Where does it go? Well, we have to evict a code page. And, well, when we evict a code page, when we try to go back into the code, now we're gonna miss for the code, and then we have to evict the data and get the code back. And do you see what's happening here? We're gonna have a lot more TLB misses. A lot more. Because now our entire TLB is just eaten up by code. So, like, we have no room for data. And in order to make room for data, we have to kick out code pages. But we actually, we need the code almost constantly. So we're going to have TLB misses almost constantly. So the answer to this is that performance would decrease because our entire TLB is eaten by code. Sound good? Right. So if we want to load, actually, hold on. So if we want to load a actual data, we would need to kick out a code page, and then we'd need to bring the code page back when we execute the code, and tons of TLB misses. Then we have to walk the page table. Remember, the page table's in memory, so walking the page table counts as an extra memory access. And memory accesses are not that great, like they're slow compared to caches. So now our performance has gone down, right? Does that make sense? So that's the first question on the virtual memory, and if I have time, maybe I'll make some more videos if people like them. This is the first time I've tried to make a video, so if you have any suggestions, then feel free. And I hope that was helpful, and if that was helpful, maybe I could make some more. Otherwise, it's like, tell me how the experiment went. So I hope I hope you found this useful, and I hope you learned a little bit about virtual memory and improved your understanding of how to do virtual memory exam questions. And good luck on the final.